Hello, Miss Kwan and all our friends. We are Group 10, and our members are Zhuohan and Jinghan, Zhou Hongfei, Wang Dong, and Yan Xi. Today, we are going to give a presentation about deep reinforcement learning methods and application. The topic we selected is deep reinforcement learning research for traffic signal control, and exact is the intelligent vehicle pedestrian lights, or IVPL in short. So for the first part of our presentation, let's welcome Peng Fei to talk about some background motivations and challenges about this topic.
The first part is background. Deep reinforcement learning has been widely studied in traffic signal control due to its potential to outperform traditional fixed-time signal control systems. Despite the promising results that indicate the superiority of deep reinforcement learning in terms of the quality of solution and optimality over fixed-time signal control, the real-world multi-modal traffic flows, especially pedestrians, are not properly consider now sufficiently investigated. Next is motivation. Reinforcement learning is the most popular method in AI-based traffic signals control due to its robust design-making capabilities. Reinforcement learning's core advantage lies in its ability to learn optimal policies through interaction with the environment, using trial and error to maximize long-term rewards. This iterative learning process enables reinforcement learning algorithms to adapt to complex and dynamic traffic scenarios, making them highly effective for traffic signal control. Deep reinforcement learning-based traffic signal studies are capable of making superior designs by leveraging the power of deep neural networks to process extensive traffic data. These studies involve observing the traffic environment, taking actions, and receiving rewards. This observe-act-reward cycle helps the reinforcement learning model continuously improve its design-making policy, leading to more efficient traffic signal timings compared to classical methods. Next is challengers. There are two challengers. One of the key challengers is developing a deep reinforcement learning-based traffic signal control strategy that effectively operates both in the presence and the absence of the pedestrians. Another significant challenger involves optimizing the interactions between various road users and accurately incorporating traffic data from the cross-box area of intersections. Additionally, the model must account for residual cues from previous cycles to optimize signal timings effectively. Next is Jinghan.
So now I'll be explaining what is deep reinforcement learning. So in deep reinforcement learning, the agent will interact with the environment to learn a task, or also known as a policy. So it is formulated under a framework known as Markov Decision Process, or MDP. So in MDP, there exist three components. The first one will be state, followed by action, and finally the reward. So what happens during deep reinforcement learning? So at time t, the agent with policy pi will take action A at state S. Then the agent will obtain the reward and will end up in a new state, which is S t plus 1. So during the process, the agent will seek to maximize the accumulated reward, and therefore it will give direction to its decision-making policy. And the general process is summed up in the equation here, which is also a Q-learning algorithm. So Q-learning algorithm is a value function of taking action in states under policy pi. So during Q-learning algorithm, the Q values are stored in a Q table. And the Q values are also constantly updated using temporal difference learning formula satisfying the Bellman equation, which is shown below, where the new value is updated by the existing value plus the learning rate multiplied by the target minus the existing value. So there are also problems that arises when we use Q-learning algorithm, where the Q table does not have enough memory capacity and resources to store and retrieve the large table. But no worries, we can use deep Q network to tackle this issue. So in the deep Q network, it will approximate the Q learning algorithm with deep neural networks. So there exist two components. The first one is the target network, which will keep the learning of primary network stable and avoids potential oscillation in training. And for the experience replay, which is the second component, it will break the sample correlation and make use of individual experiences multiple times. But then deep Q network also comes with a problem of overestimation bias. But we can also employ a double deep Q network to resolve this issue, which will be explained by Yancy later. And moving on, in the intelligent vehicle pedestrian light, there exist three components of deep reinforcement learning. The first one is state, which affiliates to the arrival of individual vehicles and pedestrians in a junction. And next is the action, which will decide the green time duration for each activated phase when pedestrians are present or when pedestrians are absent. And next, which is the reward, which will be divided into two components as well. The first one is the general reward function will minimize the waiting time for both vehicles and pedestrians. But sometimes this is not practical. So the extended reward function was created, which takes the weighted sum of vehicles rewards and pedestrian reward. So at every time step t, the rewards are collected from residual queue and at the crossbox area. Next, I'll pass on my presentation to Yancy.
In this part, I will talk about the application of the double deep Q network for traffic signal control. Traditionally, RL actions are supposed to select a specific traffic signal phase for a fixed duration. For example, in a two-phase intersection, two actions like NS green and EW green are defined each for 5 seconds. After the action execution, either MS or EW, RL can keep the green or switch to the next phase. In the proposed methodology, the phase selections are rule-based, while RL decides the duration of the selected phase. Step 1. Initialize the primary network and the target network with random parameters. Then create a buffer memory to store experience samples. Step 2. The simulation runs for a warm-up period. This allows vehicles and pedestrians to reach the intersection and form queues at the incoming approaches. Step 3. The orders observe the intersection state and identify the direction, either NS or EW, with more congestion. The direction with the highest delay, based on the number of delay users, both vehicles and pedestrians, is given the green signal first. Step 4. They check for the presence of pedestrian in each pedestrian area. If pedestrians are detected, the pedestrian light in the selected direction are also activated. Otherwise, the green light is activated only for vehicles. Step 5. The intersection state is then fed into the primary network, which returns the value QSA for the corresponding signal phase. Step 6. The KE greedy strategy is employed to balance exploration and exploitation in primary network. Step 7. The optimal Q value is derived using the following approach. And step 8. Execute action and update target network parameters. To train the DDQN algorithm and find the optimal policy, the simulation needs to be repeated for thousands of episodes. This extensive training helps the algorithm learn effective traffic signal control strategies. Moving on to model implementation, I introduced IVPRR2, Intelligent Vehicle Pedestrian Light Model. It features an extended reward function. On the other hand, IVPRR1 lacking the extended reward features found in IVPRR2. Next, they do model performance testing by comparing IVPRR2 with fully actuated vehicle pedestrian light. Now I will pass my presentation to Wang Dong.
For this part, dataset overview. Location: isolated intersection within the Australia Integrated Multimodal Ecosystem testbed located in Melbourne, Victoria, Australia. And data type: real-time traffic data of road users captured from Grid Smart camera installed at intersections. Here are 3 scenarios were explored. The first is high rush hour excluding pedestrians. The study focused on right-turning vehicles during peak hours. The advanced model, IVPL-R2, surpassed its predecessor by reduction travel times and cure lengths by about 9.45% and 12.06%, respectively, after extensive training. The second is mixed traffic environment, aimed to balance the signals for medium vehicle traffic and high pedestrian volumes. IVPO-R2 showed modest vehicle flow improvements, but significantly better pedestrian movement reduction, travel times by roughly 9%. The third is high demand traffic. In extreme traffic conditions, IVPL-R2 effectively managed both vehicle and pedestrian flows, achieving reductions in travel times by 16.5% and 3.5%. This research highlights the potential of deep reinforcement learning to dynamically adapt traffic signals controls, enhancing flow and safety across various conditions. Such funding are crucial for smart city initiatives aiming to optimize urban mobility. Next to 周涵。
Okay, so next I will talk about some of our potential insights and the research significance. So for this research, we summarize the 3 key points of its objectives. That is, the first is to achieve real-time control of both the vehicles and the pedestrian flows at an isolated intersection in cities. Thus, alleviates traffic congestion and further enhance urban traffic efficiency, and also reduce the physical and mental pressure for road users. And for significance, the most effective optimization for urban traffic, it can be used in developing diverse travel agent system to provide multiple options for urban commuters. Through dynamic data management and adjustment powered by deep reinforcement learning approaches, people can select less congested paths to reduce commuting time. Thus help to improve the efficiency and productivity of whole community in many ways. This study could be also be a component or a basis in developing more advanced algorithms and integrate them with emerging technologies like Internet of Things or industrial intelligence in future works, which will lead to more efficient systems for real-time managing. And this study provides a perspective from traffic control, and as for broad applications, there are various scenarios which require dynamic resource allocation and management to elevate the productivity, such as the customized efficient workflow management and self-driving systems, crowd control, and development of industrial robotics, and also the optimization for manufacturing process. So that's all of our presentation. Thanks for your watching.